This section is about Lewis acids and bases. So a Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. Lewis base is just like a Bronsted-Lowry base. It donates electrons. In the case of the Lewis acid, the acceptor is not a proton. It can be a proton. That's also considered a Lewis acid, but it can be something else. And I'll talk about what those are specifically in just a moment. Both of those donate 2 electrons. The electrons can either come from a lone pair, as in the hydroxide below, or the methanol lone pair, or it can come from the pi bond. The pi bond and the alkene below can donate electrons to a Lewis acid. The Bronsted-Lowry base donates to a proton. The Lewis base donates 2 electrons to any electron deficient atom, including a proton. Lewis acids, these are capable of accepting a lone pair. All Bronsted-Lowry acids accept a lone pair, except for those are all protons, the Bronsted-Lowry. All Bronsted-Lowry acids are Lewis acids, but the reverse is not necessarily true. Lewis acids don't have to be Bronsted acids. They can be other atoms besides protons. Common examples of Lewis acids are in 3A, in column 3A of the periodic table. That's boron and aluminum, as I'm showing you before. These don't have a filled orbital, and so they can accept a pair of electrons to make a full octet. And we'll see an example of boron doing this a little bit later on. And throughout the course of the year, we'll see aluminum doing this as well. Lewis acid base reactions, they follow a general pattern of organic chemistry, and that general pattern is that an electron-rich species, a Lewis base, reacts with an electron-poor species, which is the Lewis acid. Essentially, this is positive attracts negative. The Lewis base has got a pair of electrons. This is negative. The Lewis acid has something positive with regard to its ability to accept electrons, and so it's a positive attracts negative. Most of organic chemistry is positive attracts negative, and I'll be pointing this out to you over the course of the year. The Lewis acid is also called an electrophile. The Lewis base is called a nucleophile. In the case where the Lewis base is grabbing a proton, we call it a base or a Bronsted-Lowry base, typically just a base. But in the case where it's something other than a proton, we call it a nucleophile. BF3 is a common example for an electrophile, a Lewis acid electrophile, and so we show the reaction with water below. In this reaction, the Lewis base accepts, the Lewis acid accepts a pair of electrons from the Lewis base, and so we have an arrow indicating that a bond is being made. In this particular case, no bond is broken, and so we only have one pair of electrons because we only have a bond being made. Once we make the bond, we have to recalibrate our charges on the atoms that are there, so we have to figure out whether we've changed formal charges, and in this case we have the oxygen is plus charge and the boron is a minus charge. And so we're going to need to be very aware that when we make and break bonds, we have to recalculate the formal charges of the atoms that participate in the reaction. So there are other examples of Lewis acid, Lewis base reactions. In the reactions below, we see that Br minus is reacting with the carbocation, which is the Lewis acid, to form a new carbon-bromine bond. This is Lewis acid base. The bromine minus, the bromide, is the nucleophile, and the electrophile is the carbocation. In another reaction that we're going to see in organic 2, the chlorine of chloromethane forms a bond with aluminum, and so the aluminum now has a negative charge, and the chlorine now has a positive charge. These are Lewis acid base reactions. Again, positive attracts negative. About 90–95% of what we're going to talk about in this course in terms of reactions is positive attracts negative. And so we have to figure out where the positive is and where the negative is so that we can predict where the reactions will be. In many Lewis acid-base reactions, one bond is formed and one bond is broken, in which case we have to draw 2 arrows. When we draw the products, we have to make sure that we identify the Lewis acid and Lewis base first, and we draw a curved arrow starting at the Lewis base to the site where the Lewis base is going to make a bond to the Lewis acid, and we show arrows to break bonds, as I've talked about before. For acid-base reactions, we're going to talk about them generally for other kinds of reactions as well. We're going to have to recalculate formal charge every time we make and break bonds. And so here's an example of a Lewis acid, and this is actually a Bronsted acid as well. This is a reaction of cyclohexane with HCl. the pi bond of cyclohexene grabs the proton from HCl, and the electrons that were there to make the hydrogen chlorine bond stay on the chlorine, so we have the arrow indicating that. So the Lewis acid, the HCl acts like the Lewis acid, and the cyclohexene pi bond is the Lewis base. And that pair of electrons grabs the proton. It generates a carbocation when that proton is made. The HCl bond breaks, and so we show the arrow indicating the electrons are staying on the chlorine to form Cl minus. And because we make one bond and break one bond, two arrows are needed, and so we show two arrows in this particular reaction. I've been showing arrows for acid-base reactions in the past, and this is a real similar kind of reaction. I want to point out to you that I think it's in chapter 9 or 10 we're going to see exactly this reaction. We're going to call it an electrophilic addition reaction. But we're going to see these types of reactions all year long, and so you really need to practice a lot from the sapling, but also from the homework assignments. I'm not going to give homework assignments from being able to do all the problems in the back of this chapter, and you should be doing all the problems in the back of all of the chapters.